this morning is from Laura, and she's going to tell us about phase estimation of local Hamiltonians on NISQ devices. So continuing with the please.
Okay, morning everyone, and thank you for coming to my talk. I'll be outlining the results from our paper, Phase Estimation of Local Hamiltonians on NISQ hardware. This work was done as part of my PhD at UCL with my supervisor, Toby Cuthbert, and as part of a startup Phasecraft with Joanna Bush and Joel Klassen. This is the basic structure of my talk. I'll spend the first half explaining the background to our paper. First bit of background was on NISQ devices. This is from an earlier paper of ours, and then the general recap of quantum phase estimation is from the literature in general. And then in the second half, I'll be going through the results of our paper. So, review. So our paper has one central motivation. We're trying to assess whether there's any possibility, even in principle, of performing quantum phase estimation experiments on near-term hardware. More specifically, we're focusing on performing phase estimation on local Hamiltonians, a class of Hamiltonians which includes spin models of ferromagnetism, the Fermi-Hubbard model, etc. So the first preliminary section is going to introduce our mathematical framework for describing NISQ devices. This model is going to include any device where 2-qubit gates is something that you can perform by evolving under some hardware-native 2-qubit interaction. This is going to give us a continuously parameterized set of 2-qubit gates to work with. This enables the use of pulse-efficient compilation methods, which minimize the total duration of circuits containing these sort of analog gates. And in this section, I'll also go through the assumptions that we're going to make about noise in the device, and that's something we account for in all of our numerical results. The remaining preliminaries are then a quick overview of quantum phase estimation, or QPE, and the specific formulation we consider in our results. So our work is focusing on a binned version of quantum phase estimation, known as the quantum eigenvalue estimation problem, or QPE. This problem and the algorithm for solving it efficiently were set out by Rolando Soma in a 2019 paper called Quantum Eigenvalue Estimation via Time Series Analysis. So I'll recap as much of this as is necessary to explain our results. I'll explain the key features that make this suited to NISQ over like the textbook version of QPE. So yeah, then following this, I'll go through our two main results, which is an alternative protocol for solving QPE in a way that's optimized in NISQ hardware as we describe it. And then I'm going to go through the numerics that we performed for a 2D L/L spin from the Hubbard model. We're trying to estimate the impact some tweaks we made to like the QPE protocol, as well as like this access to pulse level gates can have on the feasibility of performing some minimum working example. And we, in particular, place an emphasis on the Hubbard model because of its importance within other fields like condensed matter and general classical intractability. So preliminaries, NISQ devices. Our mathematical abstraction of NISQ devices has three key components. We have a circuit model, which is on this slide, which is going to capture pulse level capabilities. Then we introduce a depolarizing error model, which assumes that noise in the device relates to the duration of these pulse level gates, and a cost metric, which accounts for those assumptions. So the circuit model is laid out here on this slide. Formally, we need to set out the connectivity of some few-qubit device by defining a set of interacting pairs of gates I, and then we're going to ensure that our circuits contain only these gates. We assume that the NISQ device we're targeting implements 2-qubit gates by evolving under some hardware-native interaction, Hij, which can be something like a ZZ interaction, ZX, and then we also need to assume that we have access to arbitrary single qubit rotations. For our analysis, we write all circuits as alternating layers of these single 2-qubit gates. And we can also write any standard circuits in this sort of form, like if you just have access to C-note gates and single qubit rotations. If you observe that a C-note gate is equivalent to e to the minus like pi/4 ZZ, up to some single qubit rotations, that means you can just like write any standard gate like circuit, like any circuit decomposed into standard gates in this sort of form. It just means you can't scale over pulse times. The specific form of the interaction Hamiltonian isn't too important. We assume in our paper it's like ZZ or ZX, but if you have any poly I, poly J, 2-qubit interaction Hamiltonian, the single qubit gates get you access to all others. So then the noise model. There wouldn't be much point in introducing the circuit model with the pulse gates if we're just going to ignore the variable time component. So the key assumption that we make about these gates is that the less time spent evolving under the interaction Hij, then the lower the probability of noise. Formally, we're going to model noise in the device as single qubit depolarizing noise, where we assume that after each layer of single 2 qubit gates, we have this error channel EL after each layer in like the full circuit. So now minimizing the chance of errors occurring is equivalent to minimizing the length of time spent evolving under 2 qubit interactions in total in the circuit. Okay, so the final thing we do here is define a cost metric that goes along with both of these assumptions. Instead of just counting the number of 2 qubit gates, now instead we draw circuits according to this total like duration spent evolving under 2 qubit interactions. So formally, we upper bound the cost of any layer L by the longest 2 qubit like analog gate that it contains, and then we're just summing up all of the layers in the circuit to get like a cost of that circuit. And as I said before, because you can write these standard gates in like this false form, as long as you have the constant times, you can use this cost metric for both. So we stick to this throughout our paper. So yeah, those preliminaries, they're set out in like a paper of ours on Hamiltonian simulation that I have in the notes at the end. Now onto the quantum phase estimation bit. So quantum phase estimation is the key subroutine in many areas of quantum information. And one of the most well-known applications is in something like TIP simulation of the factoring algorithm. Basically speaking, like the quantum phase estimation is going to retrieve the eigenphases e to the minus I phi j of a given unit U, which I've written here in its diagonal eigenbasis. In our work, we focus only on implementing a special case of QP, where we're confining ourselves to unitrines generated by a local Hamiltonian H. That is one composed of terms Hi. This is the ZZ of the fraction out. It's just like some general Pauli, usually like ZZZX. It's like, yeah, the important thing is that each term Hi is acting on some constant number of qubits. And then what we're actually looking for is information about energy eigenvalues, lambda j, that are associated with this Hamiltonian. Our hope is that this spectral information is useful in characterizing natural physical systems, which can be described by local Hamiltonians. For example, maybe you're interested in characterizing the properties of material or want some approximation to like density of states in a sense. Yeah. So within like the literature, you can find 2 broad classes of quantum phase estimation algorithm. You've got some which involve a quantum Fourier transform and some which don't. Like the textbook version of quantum phase estimation, Nielsen-Shang, type simulation, they fall into this first class, where what you're doing is obtaining information about the unitary by inducing a phase kickback on some readout register. And then the important thing is you're doing some quantum Fourier transform. And this feature, the large QFT, contributes significantly to the cost of like traditional QP, and like typically places it like well outside the range what you would think of when you think NISQ applications. But interestingly, there are modified versions of QP that replace this QFT step with just classical post processing. And this makes it much more NISQ friendly. So the basic building block of the second class of algorithms is shown here. You have some control register, you compare in a plus state, and then you're doing this controlled evolution under a unitary for some time t. And then you're measuring the observables x and y, estimating them, and that's letting you sample from this time series function, g of t. Then the second class of algorithm is going to apply like classical post-processing methods to this time series function, and obtain information about the spectrum in that way. So some algebra shows you that the time series that is outputted by the circuit I just showed you is the sum over these terms, e to the I phi j t, and this coefficient here that depends on the state that you're inputting or not, and also its support on the eigenvectors. Throughout this talk, we'll just be thinking of this rho naught as like the maximum mixed state, so this coefficient is just going to be proportional to 1. But then if you take the Fourier transform for this function, note that you get like this following spectral function, which has these nice peaks at eigenvalues of h. And I include this slide to show you that just in principle, this function, this time series g of t, contains the spectral information that we're after. And now knowing this, it's the job of specific QP algorithms to retrieve this information efficiently. And if we're going to do that, like any protocol is going to have to satisfy a number of constraints. We don't want to perform exponentially many quantum experiments, so we're only ever going to be able to sample from this GFT a polynomial number of times to k. Secondly, the largest of these times needs to be upper bounded by some capital T to ensure that the circuit for GFT contains a polynomial number of gates. And in general, the circuit for GFT is not going to be efficient for arbitrarily large t. So this is an important restriction. And then finally, any protocol that does some QP with this thing is going to have to find a way to reckon with the fact that it's going to be up to exponentially many signals, up to exponentially many frequencies in this signal. Unlike in the case of like classical signal processing, where in the literature you typically assume that you have a polynomial number of those number of frequencies contributing to this. But we'll see that the binning bit of the next QP algorithm I introduce resolves this neatly. Okay, so this is the final bit of my preliminaries, and this is going to be like my recap of some of this quantum eigenvalue estimation problem. So all of the constraints that I outlined are satisfied by Soma's bin phase estimation algorithm Q. It's a modified QP algorithm outputs a bin version of the spectral information, and in our paper we formulate it in this way. First, we take some Hamiltonian H, input state for a null, and typically, again, it's like going to maximally mixed state, but in the most general case, you have control over it. And then we have some precision parameter epsilon and a confidence C. And now the binning bit, we're going to have to choose some bin width, eta, and a bin indicator function. So the bin width is going to determine the number of bins, and this bin indicator function you can roughly think of as delineating the shape of these bins. This function has some things that it must have compact support, and it's got to obey this like normalization condition here. So it's much easier to parse this input section with, I think, a picture. So this illustration shows what the problem looks like if, say, you want 6 bins. Ignoring the colored functions for a moment, those are the indicator functions, but if you look at the x-axis on the left, this is how we bin the spectrum. It goes from -1/2 to 1/2, and all of these omega j's, these are the centers of the bins, the eigenvalue estimates that we want. And we have an indicator function fj centered around omega j for each bin, and this indicates whether for some omega you're in the bin or not. So it's 1 if yes, 0 no. And now if you look at like the color functions here, that's what each of these are. On the left is like this perfect rectangular indicator function that's literally just doing that. So just flipping back to the problem for a sec. Okay, yeah, sorry. So yeah, flipping back here, the goal is this vector P. And now if you keep that picture in mind and look at what this is, you can see that if you use the sharp indicator functions that I have on the left and maximally mixed input state or not, then each of these PJs is like literally just counting the number of eigenvalues in each bin, and you're getting like a problem that's a perfect bin of the spectrum. And any algorithm that solves it, it outputs with confidence C, a vector Q is actually close to this. So returning to the illustration now, you see on the right, I have another set of like indicator functions that they satisfy the conditions that I outlined. But in contrast, these are from bump functions that have like been used to smooth out a rectangular perfect binning function. And they overlap and they extend to the neighboring bins, but they do still satisfy the conditions. And what happens with that then is that you have like a slightly different interpretation of like this P as a perfect like binning of the spectrum. But in Soma, in this paper, he shows that even with that, you can still use Q to estimate observables that depend on like the eigenvalues and with these functions. And in our paper, we introduced another application of Soma's Q with these smooth binning functions. So you can use it to solve a problem that we call like randomized quantum eigenvalue estimation problem, which is like a randomized binning of the spectrum. Our proposed application is efficient like the fraction of misplaced eigenvalue number of bins. Yes. So yeah, that's like the problem as it's set out. And then again, get on to the algorithm that Soma proposes solving it. And when I do this, you'll see why we actually have to use these smooth bump functions and can't use the perfect rectangular ones. So to construct Q, at least from our formulation of the problem and the properties of like the spectral G of omega and the indicator functions F of omega, with a little bit of algebra, you can show that you can express P of omega as a convolution between G and F. We've got here. And then one has to make a subtle shift to considering periodic versions of these functions. You can do that because of the binning, because of the promise about the spectrum being between -1/2 and 1/2. You can express both of these functions as Fourier series, plug them into the expression for P of omega, and get the following finite sum for P of omega that's expressed only in terms of like a thing measured with a quantum circuit G of T, and something you just know from the bin indicator functions you picked, and therefore the coefficients. So the key thing now is to truncate the sum. Summa shows that, like, for the choice of f of omega in a negative function in this paper, you can truncate the sum after a polynomial number of terms, because and still ensure that that this Q, the truncated one, is epsilon close to P. To construct an indicator function like that in general, you can smooth out a perfect rectangular one with some sort of like compact like bump function, and making it smooth ensures that the Fourier coefficients fall off fast enough, truncate this, and get a nice finite expression. I'm going to get into my background now on time, so I can count my results. The first of these is our protocol for performing this, doing this time series in a pulse efficient manner. So we get an alternative circuit for GOT that's going to minimize the runtime as I defined it, and then we're going to do some numerics on the QT spin from the model. We also have an alternative bin indicator function that we tried out, which isn't asymptotically optimal, but like works better in like our numerics and like a NISQ sort of range. So our protocol is going to take any k-local Hamiltonian written in this form, and it works by introducing either control and I dash for each term I. We define this augmented Hamiltonian, pair a maximum entangled state of the control space, and then we perform a time dynamic simulation of evolution under this augmented Hamiltonian. This can be done with the Trotter formula to break it up into local gates. Then we disentangle on the control qubits, measure observables x and y's before, and you can verify easily enough that this gets you out GFT. So now, to show this is pulse efficient, it's just like a straightforward application of some of our previous results on Hamiltonian simulation. So to implement some generic U of t with the Suzuki-Trotter formula, we have t over delta steps of this like thing in the brackets here. These breaking it up into these local gates, and then you need to decompose these as well. And then at this stage, if we were to apply a cost metric to it, the runtime is just number of Trotter steps times the most costly local term in Trotter decomposition. Still completely generic. It's the choice to either use standard or pulse efficient methods to implement these local gates that gets you different runtimes. And potential gains from the pulse efficient compilation bit rely on taking advantage of the fact that in a Trotter simulation, this delta has to be sufficiently small. In our previous paper, we explained how to decompose these terms into circuits whose cost remains proportional to delta, but with some polynomial overhead k associated with the locality of the term you're decomposing. And in contrast, if you only have like standard CNOT gates and such, the best you can do is something on order 1, because you can't scale like the pulse time, it's just like a constant. So if we substitute that into the previous expression, increase the locality by 1, we can do control qubits, you get the following asymptotic runtime for both cases. And now we have like one final step to write in terms of target simulation time and Trotter error. The previous result, like expression, it diverges as delta tends to 0. So you just choose the largest, like the minimum number of Trotter steps, largest delta that gives you the Trotter error you want. Plug that in, and you get the final asymptotic expression for the pulse efficient and the standard gates. As you can see, the potential advantages of doing things pulse based, they diminish with increasing locality. Like the higher the locality of the Hamiltonian, like the diminishing gains with this. But in our case, like it's not going to be more than like 3. The difference between these overheads is pretty small, but it does appear in both target time as well as target error. And in practice, what we're hoping is that in this regime, this small motivating asymptotic difference is actually relatively large limiting circuit depths. The only way to actually then determine the significance of this is just either do actual experiments, like small scale examples of changing numerics. And in our paper, we turn to trying to do this like for a Fermi-Hubbard model. So we choose a 2D spin Fermi-Hubbard model as I've got here for this purpose. And the unencoded Hamiltonian is here in terms of fermionic annihilation iteration operators. It's got an on-site interaction, and here's the neighbor hopping interaction. Before you proceed, you've got to encode it into spin operators. And naturally enough, we use the fermionic encoding from a paper called low weight fermionic encodings for lattice models, which is written by my colleagues Charlie Derby and Jill Klassen. And this gives us a spin Hamiltonian whose highest weight term is 3 local. So we're going to break that up into two local gates. Then this is the outline of our numerics before I show you the plots. What we're doing is we're calculating the runtime of the most costly quantum circuit that we need for like keep for some bin width theta for constant error. But from the encoding, we need to perform a Trotter simulation for step 3 of our protocol of 4 local Hamiltonian. And we can do this with either pulse or efficient standard methods and compare. The simulation time, target t for this Trotter evolution is the truncation at sum. It depends on the bin with eta, the bin indicator function. So we're bounding the maximum time t. In terms of that, substituting into like an exact expression for the runtime of u dash of t that we have in the paper, and then just inverting that numeric bin getting bin with as a function of runtime. We fix the Trotter error for all of this, and then yeah, we get the following sort of plots. So these are our numerics for 3x3, 5x5, 10x10 Fermi-Hubbard model, left, center, and right. We fixed the total error for like keep and trotter, two different analytic sources, to 10% in this. And this is for on-site and hopping interactions set to 1 and 1/4 respectively. So we're plotting bin width against runtime here. This is a log plot. In red, we have the results for our pulse-based methods, and in blue, we have the standard gate methods. And that's for both the solid and the dashed lines. The solid lines are indicating a novel indicator function that we define in our paper and get bounds on for the truncation time, capital T. And the dashed lines are for the sum of functions in this paper. If you look along the thin black line of it equals 1, like the middle one, say, what's seen with this intersecting line tells you where it becomes possible to form a minimum 2-bin example of keep. So starting at the dashed line in the middle here, representing standard compilation for your local trotter steps, original bunk function, you can see that the switch from pulse-based methods buys you a little bit like this memory, gets you down from something like maybe around 10,000 to 1,000, still not NISQ. And then we have a simple tweak of the bin indicator function we use to something that's not asymptotically optimal, but has better constants. And we see that this like brings it down again to like the final red line. It's like getting it down to something more towards 100. So this story is repeated across the parameter range we're looking at here. You'll notice in the dashed and solid lines have different slopes, and they cross over at some point later on, which is what we expect because, as I said, the original indicator functions, those are the ones that are asymptotically on that cutoff time, not ours. But as we hope, this asymptotic behavior doesn't like kick in yet for like the range we're interested in. So the shading in the background, that's for noise. That goes back to the noise model I set out. So we're assuming like a single qubit depolarizing noise channel, and using that, we calculate a simple bound on the noise parameter Q in terms of target stochastic error and the runtime. So we assume that we're measuring an observable at the end of the circuit, and then we're bounding like the error in the measurement of that observable. We're upper bounding that by the probability that no error occurs at all. So it's just like a quite trivial error bound. And from that, we work out the following inequality. And then we invert this and reframe the question. So now it's like, okay, we need to run it for some runtime to get the number of bins we want for a certain error. How good, like what is this Q? How good does our hardware have to be? And see just more results. This is for total error 5%. So now the shaded regions go from like that Q noise parameter 10 to the -5, the darkest, to the -9 at the lightest. And this, for example, means that on the second plot here, if you want 2 bins, error less than 5%, including keep error, trotter, now the stochastic error, the hardware needs to have a depolarizing noise parameter no worse than 10 to the -5. So including this trivial noise bound is another way we try and gauge how significant the differences between these lines are. We view this as the best way to approach the question in like the framework we set out. Like the raw numbers of runtime make the most sense when you interpret them with respect to how they impact this noise parameter. Each of these shaded regions let us interpret this runtime as like an error budget for some underlying hardware and like deduce like what this noise rate should be if we wanted to actually do these kind of experiments. So that brings me to like my conclusions. So this is like our main conclusion. It's just that the combination of like these tweaks like pulse efficient compilation methods, adapting the algorithm a little further to this, but like changing the binning function and things like that. Although these small changes like they add up and they can make a substantial difference in like the sort of noise rates that you estimate for what your hardware model needs to achieve to make this like a NISQ type of algorithm. Of course, this is up to like some important caveats, of course. Like all of this is assuming our device model is reflective of actual hardware. Pulse access is definitely something that's increasingly available. Like IBM have all their open pulse services, and like there are experimental papers that I have references here that do demonstrate like on actual hardware this relationship between like gate duration and fidelity. And it has been used to like actually, fit more trotter steps in like some experiments on like actual IBM hardware. So that gives me some optimism, I think. But to mitigate that, there's also like, we make generous connectivity assumptions that we talk about more in our paper, but we do think about it. Essentially, we show in our paper we can only actually fit like a spin list from a hardware model neatly onto planar hardware. We can only just really single spin sector, but you can get all the ancillas that you need, the encoding and the control ones I introduced onto a basic square lattice without having to end up doing swaps all the time with other steps, but not so if we want spin vectors. On the other hand, all our numerics rely on these bounds to the simulation time that in practice could be quite loose, meaning that maybe we'll get a much finer grain of the spectrum for this runtime and error rate than our plots indicate. At least that's my hope. We also have not looked at any error mitigation techniques, which is definitely something we could explore in future. Another point for more optimism is a depolarizing noise model is actually too specific considering the trivial error band we ended up using in our paper. It actually applies to like any single qubit error channel that has like this relationship between like the duration of the gates and error probability. So that's one upshot. We also chose the Fermi-Hubbard model as like a specifically challenging example. Like it definitely has more of an overhead for pulse-based methods than say a two-local spin Hamiltonian. So yeah, I think for these reasons, I'm relatively optimistic about maybe performing like QCTIP in like on NISQ hardware. I think our work shows that in practice, this is what you can leverage to get closer to performing interesting demonstrations, even for algorithms they don't typically think of as being NISQ friendly, like quantum phase estimation. And it's not just all like PQE in the near term, hopefully. So that's my talk. Does anyone have any questions?
Well done fitting all that in the time. Questions? I can see a couple of hands already. Let's have Adam and then I'll go behind. So go.
Yes, so the traditional form of QE can be used for probability eigenstate preparation. Does that scheme as well?
As in preparing like the eigenstate.
Yeah, so the energy measurement will, if
you know,
get the right energy for that to the eigenstate.
I think it would. Sorry, I have to think about that a bit, but I think it would. Sorry, yeah. Yeah. I'll
think about that, right?
I was wondering what hardness results you know about.
Okay. Oh, so there's some. We have a bit on this in our paper actually. Like there are really interesting hardware results on things like, you know, like the randomized QEP thing that is randomized because of hardware, because of hardness results. Like I think it's B sharp, one of the hardware for like actually probably like getting out a discrete density of states like perfectly. So I think, yeah, you can only like do this. You have to fudge it somewhere with these kind of like smoothing functions or the random thing that we end up doing.
I guess because so I know the results center that link say.
Sorry.
The results center that link the QEP say on phase estimation require the bin width suddenly be lower than the gap to resolve at the same time. I was wondering if I go for one, do you know how small of a bin width you would have to make your
So I think the thing is that you have exponentially many eigenvalues as you go with system size. So your bin has to, if you want to do it perfectly, that bin width needs to go exponentially, like fine. And like the overhead in the algorithm is like one over the bin width, so it blows up there. So that's, I think, the essential hardness. Oh, right, yeah. For the gap. Oh, yeah, sorry, I was thinking of a different, like if you want the full spectrum, then not just the gap. Yeah, if you have like comments on that, like how the gap scales, then like, yeah, I think this was really interesting.
Let's check. Do we have any online questions? No? Okay. Let's thank Laura again for a fantastic talk.